So, Samuel, we're moving beyond linear models. What's the big deal about artificial neural networks?
Well, Alfred, linear models like, y equals mx plus b are pretty straightforward. But they can't always capture complex relationships.
Like what?
Imagine predicting house prices. Size, location, and maybe even the age of the house might be important factors. A linear model might struggle to capture the intricate ways those features affect price.
So, neural networks are better at that.
Exactly. Neural networks use layers of interconnected nodes to learn complex patterns in data. They can discover nonlinear relationships that would be hard for linear models to grasp.
So, how do they work this magic?
Think of it like a series of interconnected filters. Each layer does a transformation on the input data, learning the right features along the way. This iterative process is really key.
So, like the training process?
Yeah. The model goes over the data, adjusts its connections, and learns the relationships. We're using gradients to adjust these weights, and this process is all about minimizing errors.
And the diagram shows that?
Right. It shows how the desired output is compared to the actual output. The loss function quantifies the difference, guiding the adjustments.
Makes sense. So, we're using this for temperature conversion now?
Exact.
So, we're not limiting the shape of the function as we do with quadratic models anymore?
Exactly. That's the crucial improvement. We're letting the network learn the optimal function form, not just a predetermined one.
So, how is this different from what we did last chapter?
In the previous chapter, our models had a fixed structure. Now we're using a flexible neural network architecture, letting the network itself discover the most appropriate function for the problem.
Interesting. And you said we're leveraging PyTorch's capabilities?
Yes. It handles the gradient calculations for us, so we can focus on the model structure and training process. This is a common workflow in machine learning and makes it much easier to create and train complex models.
This is helpful. This is really great. So, this is a step up from what we've done previously.
Absolutely. We're going beyond simple models to capture complex relationships. This sets the stage for more sophisticated machine learning tasks.
So, neural networks, they're like simplified versions of our brains, right?
Well, not exactly. They use similar math, but the biological mechanisms are very different.
Okay, so what is a neuron in this context?
It's a fundamental building block. Think of it as a simple calculation.
A calculation? Can you give me an example?
Sure. You take an input, multiply it by a weight, add a bias, and then apply a nonlinear function.
Whoa, hold up. Weight and bias? What are those?
Imagine you're trying to predict something, like house prices. Weight is like how much a feature, like square footage, influences the price. Bias is a constant offset.
So, it's like a formula.
Exactly. And that nonlinear function is crucial. It adds complexity.
Like, what kind of function?
A hyperbolic tangent, or tan, is common. It squashes the result into a range between -1 and 1.
So, the input goes through a linear transformation, and then a nonlinear function? That sounds important.
It is. It allows the network to learn complex patterns. And these calculations can be stacked, creating layers of neurons, which is why we call them neural networks.
So like a bunch of neurons together?
Yeah, many neurons working in concert to perform increasingly complex functions. It's how you train a network to do stuff like recognizing images or playing games.
How would you use this with house prices?
You'd feed in data, like square footage, bedrooms, location, and the network would learn the relationships. Eventually, it could predict prices.
Interesting. So the weights and biases change. That's how it learns, right?
That's right. The network adjusts these values based on the input data to get better predictions.
So the whole system is about making predictions?
Exactly. By analyzing data, neural networks can make complex predictions.
And the image or games, that's all just more complex prediction problems?
In a way, yes. Recognizing images, playing games, all come down to predicting outputs based on inputs.
Okay, Samuel, so multilayer networks, right? How does that actually work? It's a composition of these functions, you said?
Yeah, it's like building with Legos. Each layer is a step in processing. One output becomes the input for the next.
So, these pound symbols? What are those?
Those are functions, like mathematical operations. Think of them as transforming the data as it moves through layers.
And these W and B things, matrices and vectors? That's where the magic is, right?
Exactly. W are the weights, and they're matrices, allowing us to adjust connections between different layers. B are biases, shifting the data for a smoother processing.
Okay, a matrix for a whole layer? That's clever. So, what does it mean in practice?
A single weight would adjust a single connection, but a matrix allows us to adjust many connections at once. Makes it way more efficient.
So, what if you need to change certain nodes in a layer?
You change the corresponding values within the matrix. It's all connected. It's flexible, very powerful, and very efficient.
How do you visualize it? That figure 6.3 is a bit abstract, isn't it?
Well, imagine a pipeline with different departments. Each layer is a department, transforming the data. The output of one feeds into the next. The W are the adjustments they make to handle each new input.
So, you're processing information in stages?
Precisely. The output of one layer is the input to the next. Each layer is adding complexity and extracting different features from the input. It really boils down to building layers of interconnected functions. Very powerful.
What about different applications?
Lots of things. Image recognition, natural language processing, even game playing. The possibilities are vast. A multi-layer network helps create increasingly complex decision-making systems.
So, Samuel, you were saying neural networks' error surfaces are different. Can you explain that?
Yeah, it's a crucial difference. Linear models, have this nice, smooth bowl-shaped error function. One clear minimum.
So like finding the best fit is straightforward.
Exactly. Like aiming for a target. But neural nets, even with the same loss function, are a bit more complicated.
More complicated? How so?
No single, perfect solution. Think of it like fitting a puzzle together. Lots of possible ways to get close to the right picture.
So, lots of local minima?
Potentially. Each parameter isn't aiming for a single perfect value, but instead a group of values working together to get a good output. Kind of a collective effort.
So, the error isn't just one valley, but a whole mountain range?
Precisely. And the activation functions play a significant role. Those nonlinear elements.
What's the practical significance of this?
Well, it's like trying to tune a radio. The optimal settings aren't so clear-cut. You twist knobs to hear the faintest signal.
And where and how imperfections manifest is
Arbitrary. You might adjust one knob, and it alters another aspect of the sound.
So, it's not always intuitive, right?
Yeah, it's often a trial and error process. It's more of an optimization, rather than a direct solution.
Like tuning a really complex radio.
Exactly. And the theory is fundamentally different from the smooth single minimum approach. It's more about the ensemble, rather than one single perfect parameter.
So, training a neural network from a mechanical perspective is still about parameter estimation. But the theoretical foundation's a little fuzzy, maybe?
Absolutely. You have to look at how the parameters all work together.
Okay, Samuel, activation functions. Crucial, right?
Absolutely. Think of them as a gatekeeper.
A gatekeeper? Like a security guard?
Exactly. They control the flow of information.
How so? We've got this linear operation. What does the activation function do?
Well, it adds nonlinearity. Linear operations, they just scale and shift things.
So no curves, no bends. Just straight lines?
Exactly. But activation functions create curves. They make the output different at different inputs.
That's crucial for the inner parts of the model.
Absolutely. It lets the model approximate any function.
And at the last layer?
There, it caps the output range.
So like a limiter?
Yep. Keeps outputs within a sensible range. No runaway scores.
Like a 10-point scale, for example. But what if the model outputs 11?
Then, the activation function caps it at 10.
Got it. So, you've got capping functions?
Like hardtan. A simple one, just sets values outside the range to the limits.
And others like sigmoid?
Yeah, sigmoid, tan. They're more complex but also quite useful.
So they compress the output, right?
They create a curve that asymptotically approaches the boundaries.
And what's the advantage of that?
It gives a particular sensitivity in the middle. Garbage trucks are way out there. Good dogs are at the other end. Bears are in the middle, very sensitive.
So it's like a gentle slope for good dogs and bears, but very steep for garbage trucks.
Exactly. Small changes to input values in the sensitive range result in big changes to output. Conversely, you need major changes for things far from that range.
Interesting. So it helps with classification, right?
Exactly. Keeps things separated effectively, like good dogs, bears, and garbage trucks.
So, Samuel, you were saying ReLU is a top performer. Why is that?
Yeah, it's really simple and surprisingly effective. It's basically a linear function for positive inputs and 0 for negative.
0 for negative? That sounds a bit abrupt.
Precisely. That abruptness, that rectification is key. It avoids the vanishing gradient problem that some other functions have, particularly in deeper networks.
Vanishing gradient problem? Can you explain that?
Sure. Imagine a very complex neural network. During training, gradients from the output need to propagate back through all the layers to adjust weights. If activation functions are too squishy, the gradients get smaller and smaller as they go back, eventually becoming almost 0. That halts learning. ReLU, being linear for positive values, avoids this.
So, hardtan and softplus, are they somehow less effective?
Well, hardtan is a harder version of tan, right? It's more linear, with a hard cutoff. And softplus, it's smooth, but it has its own trade-offs in terms of computation. ReLU is the sweet spot, often.
Leaky, what about it? A more gradual transition?
Exactly. Leaky ReLU has a small positive slope for negative inputs. This helps with the dying ReLU problem, where some neurons in a network might never activate, essentially becoming inactive during training. It's like adding a little bit of leak in a pipe. It helps flow.
So sigmoid, it's out of favor? Why?
Sigmoid, while important historically, saturates quickly. Like it gets stuck near 0 or 1 for extreme positive or negative inputs, with limited impact. It reduces the gradient, making training harder.
Right, makes sense. So, the choice of activation function depends on the specific task?
Definitely. If you need outputs in a 0 to 1 range, like probabilities, sigmoid might be the way to go. But otherwise, you're probably better off with ReLU or a variant.
Thanks, Samuel. Really helpful. So, activation functions, they're crucial. Tell me, Samuel, why is nonlinearity so important?
Well, Alfred, imagine a network without it. Just a bunch of linear transformations. It's like a really simple calculator. You can't get much out of it.
So, what's the magic of nonlinearity?
The nonlinearity lets the network approximate more complex functions. It's like having a tool that can learn curves and not just straight lines.
Okay, got it. Differentiability. Why is that a must?
Crucial for backpropagation. You need gradients to adjust the weights properly, and that relies on the function being differentiable.
So, if it's not differentiable, the whole system breaks down?
Yeah, it either becomes a linear model, essentially useless, or training becomes practically impossible.
And these sensitive and insensitive ranges? Explain those.
Activation functions usually have a range where changes in the input create noticeable changes in the output. That's critical for learning.
So, think of a lever, right? Lever's sensitive to pushing, pulling.
Exactly. But there's also a zone where pushing and pulling doesn't significantly change the output. Like pushing on a very stiff lever, it won't move much.
Interesting. So, backpropagation works better on the sensitive side?
Precisely. The gradients are strong there, making weight adjustments easier. The insensitive zone? Gradients are near 0, learning stalls.
Okay, so you're saying combining linear and activation units is powerful?
Absolutely. Different inputs activate different units in different ranges. Learning for those sensitive units is pretty much like a linear function. So, it's efficient, and you can approximate complicated functions.
It's all about finding those sensitive areas, right?
You're getting it. And that's why activation functions are so important. The network can adapt to a huge range of inputs.
So, what happens when inputs are in the insensitive range?
The network's parameters associated with those neurons won't be very heavily affected during the learning process.
Learning will focus on those sensitive units, right?
Exactly. Leaving other units more or less undisturbed. That makes learning far more efficient.
So, Samuel, you're saying deep neural networks can approximate complex functions without needing a specific mathematical model?
Exactly. They're like universal approximators.
Wow, that's pretty powerful. Can you give me a real-world example?
Sure. Imagine predicting stock prices. You know, complex, interconnected factors influence them. It's hard to create a perfect model.
Right. So, these networks aren't trying to understand the market, just predict it?
Precisely. They find patterns in the data, and they map inputs to outputs. They learn the relationships, not necessarily why they exist.
So, it's like a black box, right?
Well, in a way. But that's also its strength. It can deal with complicated relationships, even those we don't fully understand.
But if you don't understand how it's working, how can you trust the predictions?
That's a fair point. We need validation. We test the model on unseen data, like new stock prices. If it does well, we trust its predictions more.
That makes sense. How do these networks learn?
By adjusting the weights and biases of the neurons. It's like fine-tuning a complex machine.
And this learning process? How is it different from traditional machine learning?
Traditional methods often need a clear, explicit model. You have to specify the function beforehand. With deep learning, it figures out the best way to combine those transformations.
So, no handcrafted rules?
No, that's the big difference. Deep learning learns the rules from the data itself.
But doesn't that mean the network could be fooled?
It can, yes. Like, if the data has hidden patterns or noise, the network can be misled. So, careful dataset selection is important. You know, good quality, representative data is key.
Okay, so a lot more attention to the dataset is needed. And it seems like model complexity can grow quite a bit.
Absolutely. Deep networks have millions of parameters. And as you add layers, you can model increasingly complicated relationships. And remember, that initial example of temperature prediction.
Exactly. You could have several inputs to several outputs.
Yes, the dimensionality of the problem often gets much higher.
So, is there a drawback to this black box approach?
Well, it can be hard to interpret what the network is doing internally. Sometimes you might get good results, but it's unclear why. Understanding the why behind those calculations could be difficult. It's not always transparent.
Interesting. So, we're giving up interpretability for potentially more accurate predictions. In some cases.
In many cases, yes. But in some situations, that interpretability is absolutely crucial.
So, Samuel, we're moving from linear models to neural networks. This is a step back, right?
Yeah, in terms of the calibration problem, sure. We already know linear works. But it's a crucial stepping stone. Think of it like learning to ride a bike. You gotta start with 2 wheels.
Right. Why is PyTorch's NN module important here?
PyTorch's NN module provides tools for building neural networks. It has these blocks, called modules, that are like Lego bricks. You combine them to create different network architectures.
So, these modules are Python classes?
Exactly. They inherit from a base class, NN, module. Crucially, modules can have parameters, like weights and biases, which get adjusted during training. And they can have submodules inside them, which also track their own parameters.
So, what's the significance of top-level attributes?
The optimizer in PyTorch needs to find those parameters. If they're tucked inside lists or dictionaries, it can't find them. That's why PyTorch has nn.modulelist and nn.moduledict for organizing modules in lists or dictionaries.
And we can use NN linear?
Yep. It's essentially the same as our earlier linear model, but part of a more powerful framework. It does an affine transformation.
What's an affine transformation?
Think of it as a way to map data from one space to another. It involves multiplication and addition, similar to what we did with the linear model. NN. Linear handles that efficiently, with the important weight and bias parameters to make it fit to any dataset.
So, it's really a more sophisticated way of representing the same kind of function for more complex tasks?
Exactly, it's like a flexible template for different kinds of functions, ideal for building networks with more layers and neurons. Imagine doing a linear regression with billions of data points. PyTorch's NN modules make the task manageable.
Interesting. So, we'll be converting our code to use this now?
That's right. We'll translate our previous code, step by step, to use NN. Linear, integrating seamlessly into the wider neural network ecosystem.
So, Samuel, you're saying using __call ___ is the preferred way to interact with PyTorch modules?
Yeah, it's the standard way. Think of __call __ as the public interface.
Okay, but what exactly does it do under the hood?
It handles a bunch of extra stuff before and after the actual computation in the forward method. It's like a manager, making sure everything is set up correctly and cleaned up afterwards.
Like what? What are these hooks?
Well, PyTorch modules can have these little callback functions, called hooks. They're designed to be triggered at specific points during the process. Things like logging, or monitoring progress, or even modifying the output.
So, if I just called forward directly, I'd miss out on those hooks?
Exactly. You'd be skipping the important setup and cleanup steps. It's like bypassing the gatekeeper. You might get the result, but not everything would work properly. Imagine a company. Forward is the production line. __call ___ is the whole factory, including quality control and shipping.
What are some practical examples of when these hooks are useful?
Training a neural network. You might have a hook that logs the loss after each iteration to monitor training progress, for instance. Or a hook for visualization during the process. Even adding regularization would be possible via hooks.
So, just calling forward directly is possible, but it's discouraged?
Absolutely. It's like trying to fix a car by skipping the manual. You might get somewhere, but you risk breaking more parts. __call ___ is the prescribed method for smooth operation.
Why is this so crucial? What could go wrong?
Well, imagine a complex model. You might have multiple parts needing initialization, or cleanup steps, or special logging. You'd need a systematic way of managing these elements, and using forward directly wouldn't give you that. You'd miss out on some vital functionalities.
Makes sense. So, avoiding calling forward directly is a bit like using the proper method. For instance, for creating an object or handling a file. You're not just calling the method of interest directly, but using a higher level interface instead.
Exactly. It's about following the correct protocols and procedures. PyTorch makes this more efficient and reliable, even for complex deep learning models.
Great explanation, Samuel. Thanks for clarifying this important detail about PyTorch modules. So, we're now using PyTorch's built-in NN linear module, right? How does this simplify things compared to our custom implementation?
Yeah, absolutely. Before, we had to define all the weights and biases. Now, PyTorch handles that internally.
Okay, but how do we feed in the data? We need a batch, right?
Exactly. PyTorch expects a batch dimension as the first dimension. So if we have 10 samples, the input tensor needs a shape of 10 by 1. We use unsqueeze to add this extra dimension if the input is only a 1D array.
So this batching is crucial? Why?
Crucial for efficient computation. GPUs are super parallel. With a batch, we can spread calculations across many cores, making it much faster. Also, some models use statistical info from the entire batch, which gets better with larger batches.
Makes sense. So, we have this batching now, and our model handles it.
Exactly. The model handles batches.
And the optimization? The optimizer now takes the model's parameters directly.
That's right. Linear_modeled parameters gives a list of all the parameters. This is fed directly into the optimizer.
So, during training, we provide the batch of data and the PyTorch handles everything else?
Precisely. We pass in the model. The optimizer updates the model's parameters.
Wait, I'm getting it. So, training is now streamlined. No more manually managing parameters.
Exactly. The NN module handles the specifics. It's more concise and, in most cases, faster.
The loss function is nn.msLoss now. What's the trade-off?
We're using a standard loss function. While we could customize, MSE loss is commonly used and usually efficient.
Is there a risk we could encounter if the batch size was too small?
Yes, we might not utilize the full potential of the GPU's parallel processing. If the batch is too large, we might run into memory constraints. It's a balance we need to consider.
So, we're moving beyond linear models?
Yeah, we are. It's time to introduce neural networks.
Why neural networks now? We said linear models were sufficient for this calibration problem.
True, linear models are perfectly adequate here. But we're building our knowledge.
Building knowledge?
Exactly. This step lets us see how a more complex system behaves. Think of it as controlled experimentation.
Controlled experimentation. So what's the point?
Well, it's like learning to ride a bike. You start with training wheels, right?
Right.
Linear models are like training wheels. Neural networks are like the real thing. It's good to practice with more robust methods.
Makes sense. And these neural networks won't improve the model's accuracy here, right?
That's correct. The underlying process is fundamentally linear. So it's not about finding a better model.
Okay, so why not just stick with a linear model then?
Good question. It's not just about the immediate task. We're building our skills. It's like learning to write. We don't start with novels immediately.
Makes sense. You're saying this is a learning exercise.
Exactly. The neural network is a more powerful tool, but there's no need to be a rocket scientist about it. We learn more by practicing.
So, just because we're going to use a neural network.
Exactly. Plus, we'll avoid confusion when things get harder. This is a very important aspect of coding, understanding when tools are appropriate.
So, by making the leap, we're not just building a more complex tool for this project, but more generally building our own knowledge of how tools work.
That's a very precise statement. It's like learning a new musical instrument. It won't magically play symphonies the first time, but it enhances our understanding of music in general.
Okay, so a step in expanding our understanding, not for the specific task here.
Precisely. The next time you encounter a similar situation, you'll understand your options better.
Okay, Samuel, so we're ditching the linear model, right? What's the new approach?
Yeah, we're building a simpler neural network. Think of it like a series of connected processing steps.
Okay, so a hidden layer? Can you paint a picture?
Absolutely. It's like a stepping stone. We take our input, process it through a linear transformation, and then add an activation function.
An activation function? What does that do?
It introduces nonlinearity. It's like adding a twist. Without that, you're just doing more math on the same data, no extra information.
So this hidden layer, how big is it?
It can have more than one output node. Important, it's often bigger than our input. This extra capacity lets the model learn more complex relationships in the input data.
Why larger outputs, Samuel?
More complexity in the hidden layer allows different units to respond to different input ranges. Think of it as focusing on different aspects of your data.
You're saying this makes the model more powerful?
Exactly. It's a more robust approach to handle various input characteristics. This added dimension increases the model's capacity to learn patterns.
And how do we represent this visually? Those diagrams were interesting.
The diagrams, there are different views. The left one's a beginner style, the right one's a bit more advanced, focusing on the computations.
And the PyTorch code?
PyTorch has this neat NN, sequential container. It makes it straightforward to connect modules together. We chain the steps, linear transformation, activation, then another linear transformation to create our output.
So, basically, it takes a single input, expands it, does some processing with nonlinearity, then combines all that for the final output. Got it?
That's the essence of it. It's like building with Lego bricks, carefully arranging components to create a more advanced system.
Okay, Samuel. So we're looking at how to inspect the parameters of our neural network. Can you walk us through that?
Sure. We're checking the weights and biases in the model. Think of them as the knobs we turn to adjust the network's learning.
So, how do we get these values?
We use model.parameters. That gathers all the weights and biases from all the layers.
And what does the output look like?
It shows the shape of those tensors, like 13, 1, 1, 13. That tells us how many rows and columns each weight matrix has.
So each layer has its own set of these.
Precisely. The optimizer uses these shapes to know how to adjust the weights and biases to lower the error.
Got it. So the optimizer works with these numerical values.
Right.
More detail? How so?
It tags the weights and biases with the layer's name. For instance, hidden_linear.weight or output_linear.bias.
That's much clearer. Why is this useful?
Well, it's helpful if you have complicated models with multiple layers. You can easily identify which weight belongs to which part of the network.
Is there another way to get information about these parameters?
Yes. We can directly access specific layers, like seek_model output_linear bias, to get the bias of the output layer.
Cool. So you can isolate those specific parts.
Exactly. And you can use that to monitor things during training, like gradients.
I see. You can pull out information even about gradients.
Yes. Knowing those gradients helps us adjust those parameters to find the best values.
Okay, so that's about inspection. What's next? How do we use this to train a model?
Well, you initialize an optimizer. It usually uses the method optimd_sgd, which is gradient descent. It needs the model's parameters and a learning rate.
The learning rate?
Yes. That's how big the steps are to reach the optimal solution.
So, the training loop? Tell me more.
The training loop iterates over your data, calculating the loss, adjusting the parameters, and repeating.
And we see loss values through the epochs.
Right. They get lower over time, as the model learns to minimize the error.
What if the learning rate is too high or too low? What are the implications?
A high learning rate might skip the minimum and not converge properly. Too low, and training takes forever.
Okay. Samuel, we're looking at a neural network model for temperature conversion. So, it's predicting Celsius from Fahrenheit. What's the key takeaway from this plot?
Well, Alfred, the plot shows how our neural network fits the data, compared to a straight line.
Right, so a straight line is a linear model?
Exactly. The neural network tries to mimic the relationship between Fahrenheit and Celsius, but it's more complex than a simple straight line.
And what does it look like in the graph?
The plot shows data points as circles, and the neural network's output as XS. The line connecting the XS is the neural network's prediction, showing the model's behavior between the data points.
So, the neural network is clearly trying to hit every data point, which is potentially a problem.
Exactly, Alfred. It's overfitting. It's getting too close to the training data. Neural networks with many parameters can sometimes find patterns in the data that aren't actually real patterns in the underlying relationship.
So, if it's fitting all the noise, why doesn't it just perfectly follow the points?
That's right. And the plot reveals that it's trying to follow the noisy data. Our neural network model has more capacity, potentially more than needed to fit these data points.
A key term here is overfitting. Can you elaborate?
Overfitting means the model fits the training data extremely well, but performs poorly on new data it hasn't seen. It's like memorizing answers instead of understanding the underlying concepts.
Makes sense, the model is chasing noise. So, even though the fit appears good in the plot?
Yes, it seems good, but it's not generalizing well. It could give inaccurate predictions for temperatures outside the range of training data.
Thanks, Samuel. You've made that very clear. So, we've explored building and training models. Pretty cool stuff, right?
Absolutely. We've gone from basic concepts to using PyTorch.
It seems simple enough when we're just looking at these simple examples. But how do these concepts extend to, say, more complex problems in deep reinforcement learning?
That's a great question. The core principles are the same. We're still dealing with differentiable functions and gradient descent. It's just that the models become much more complex.
Right? Like navigating through a maze or playing a game. How does the concept of differentiable functions play into that?
Well, you need a way to measure how well your model is performing. Using gradients, you can pinpoint areas for improvement. Think of the gradient as a compass, pointing you towards the best path.
So, gradient descent helps refine the model strategy?
Exactly. And these sophisticated models become essential for games or robotics, where quick reactions and optimal strategy are key. You are essentially teaching an AI to learn by experience.
This whole idea of learning by experience is fascinating. It really feels like we are unlocking a new way to teach machines. Can you elaborate on the importance of this, especially in reinforcement learning?
Absolutely. Reinforcement learning agents don't just passively receive data. They actively interact with an environment, get rewards for good actions, and penalties for bad ones. The gradient descent helps them learn these optimal strategies through trial and error.
So, that feedback loop is crucial.
Crucial indeed. It's a dynamic process. The agent explores the environment, learns from its actions, and progressively improves its performance.
And are there any potential pitfalls? Any common misconceptions?
One pitfall is overfitting. If the model learns the training data too well, it might not generalize to new scenarios. Another is the computational cost, especially for complex tasks.
I see. That makes sense. So, while these simple examples give us a solid foundation, the real power lies in building and training models capable of tackling complex, real-world problems.
Exactly, and with more practice in PyTorch and other frameworks, you'll have a much stronger understanding of the complexities behind these models and how we can solve them.